a bunch of these. So basically, rho is going to allow us to keep track of the types that we picked when inside the for all case, the types that we picked for one side and for the other. It's a way of remembering that. Okay, with me so far? All right. So let's see if that does the trick. The answer is it doesn't. But let's see where. All right, so I could just, here, none of these earlier definitions use rho, so let's just plop rho everywhere, and it just gets carried around without being used by any of these. If I missed a spot, let me know. Oh, here, of course, we need to be careful now. Also, when I write rho is something of this form, I'm going to use the following shorthand. I'm going to write rho 1. So if rho looks like this, I'm going to write rho 1 to mean the substitution that maps alpha to tau 1, and similarly for all the alphas, for all the other alphas, pick the type on the left side. And I'm going to write rho 2 to mean the substitution that maps alpha to tau 2, where that's the second type. Okay? So that's going to be my shorthand. All right. So here then, to be careful, we need to make sure these are no longer closed expressions, right? So this term is going to have the type rho 1 of tau 1 to rho 2 to rho 1 of tau 2. You see that? Or more generally, where's Adam? We are allowing these two terms to have two different types, tau 1 and tau 2. Okay? And we are building every one of our view relations so that whenever we have view relations or E relations, whenever we have E1, E2 belong to E tau with a rho, then this guy has type rho 1 tau and this guy has type rho 2 tau. Okay? That's the slight stuff you have to be careful about here. Okay. So here, rho 1, here, rho 2. Okay. Yes?
With the argument, you still get the same tau 1 for both arguments, but wouldn't it make sense to also generalize the second one to be?
It is being generalized. So this is the argument type, right?
Yeah.
Suppose that this was tau or tau prime, and now try to read it. The argument type of the function, the argument type of this function is rho 1 of tau 1, and the argument type of this function is rho 2 of tau 1, because we're talking about the argument. Yeah, perhaps if you write this as tau or tau prime, then the 1s and the 2s don't get confused.
So it's just that we're not doing it for, like, you could think of the two functions being different and then you're relating them over.
So are you talking about, like, let's take a look at this example. Once we've applied it to rule, in the first case, we end up with rule 5 applied to true, and in the second case, we end up with int 5 applied to 0. That's your concern, right?
Yeah, but I guess if we just generalize the alpha.
Yes, we're just generalizing the alpha, right? The rho is keeping track of what the alpha goes off with. So this is allowing us to generalize that. I put rho 1 of tau here and rho 2 of tau 2 here. The argument, the actual concrete argument types of these functions can be different. If rho maps any free type variable in tau 1 to different types, then the argument of these two functions will be different. Okay? All right. Now, let's come back to this. Okay, so said let's add rows, and now we have a row coming in, and what we're going to do is this tau, so all of the free type variables in this type were mapped to something by rho, right? Now this type tau has one extra type variable than we did before. So we need to map that to the things that we've just picked for the two sides, which is tau 1 and tau 2. Fair enough? Yes. Yeah.
If rho are consistent, or by your assumption of the language is already type safe?
No, you have to, you need to know something about that, and that's exactly what I'm getting to next. But let's look at it in the context of fine. Now we're doing interpretations of open types, right? So we need to be able to handle the case where tau has free type variables. So how do we interpret alpha? What are the values that belong to alpha? Or what are pairs of values v1 and v2 such that v1 logically approximates v2 at the type alpha? Yes?
Plug in any type and it would work the same?
Well, that's the issue, right? So what do we know at this point? The only thing we know is that rho gives us a mapping from this alpha to some tau 1 or some tau 2. We know that, right? Okay.
Oh, so we can look up.
Which means that we know that this guy has to have type tau 1, this has to have type tau 2. You with me? Okay, but we know nothing else about what relationship we want between them. When are they related? And this is the thing. That's why it's when we pick two arbitrary types, right? Like in our example, when we picked, let's go back to writing it that way. Lambda alpha, lambda x alpha 5 applied to bool and true, and similarly applied to int and 0. Here, I picked a tau 1, I picked a tau 2. All right? And I gave them to this type abstraction as inputs. But after that, I have to give it an input of type alpha, right? So I'm choosing to give it true and 0. Basically, my point is here, at this point in time, I'm saying, here, from now on, consider these two completely different types to be related. So at that point, I also have the obligation to give you a set of values of the types tau 1 and tau 2 and say when they are related. So I need to have a relation R that tells me when values, so let's write this a bit more precisely. We want a relation R from something that I'm going to call rel of tau 1 comma tau 2. Is that too squished? Should I rewrite? R, so for all tau 1, tau and all tau 2, and for all R that belongs to rel of tau 1, tau 2, which I'll define in a second, we need to show that E1 with tau 1 for alpha is related to E2 with tau 2 for alpha. For J set. Okay, what is rel? Have people heard of Girard's candidates method? Okay, for those of you who have or haven't, let me just say a few words. So Girard's candidates method was basically a method for proving strong normalization for system F. All right, and the main observation, or the relation to what we're doing now is when you get to this part of your definition in system F, when you try to define the interpretation of polymorphic types, you get to pick an arbitrary relation here. You can't just pick an arbitrary relation. It needs to have certain constraints on it. Otherwise, your logical relation as a whole won't be consistent in various ways. Okay? So just keep that in mind for now. So let's figure out what those conditions are that we need to impose. So we're saying you can go pick an arbitrary relation. Let's figure out what that is. Now, this relation should map I'm going to erase this. By the way, just like I had row 1 for alpha maps to tau 1 before, and row 2 as shorthand for alpha maps to tau 2s, I'll write row R for the third component that I'm storing in there now. Okay? Again, just shorthand. Let's leave that to the side. Okay, so what is rel of tau 1, comma tau 2? I think I need one moment's digression before I do this. Since yesterday, I've been defining. Yesterday I defined these as sets of values. Today I'm defining them as relations on values, right? I just want to get one notational thing out of the way. So yesterday this was basically a member of power set of closed values, right? Yeah? Because it's a set, it was a set of closed values, so it's a member of the power set of closed values. Today we're doing relations, so we want that, right? Okay. Furthermore, the values that I put in here, I want them to be well typed. So instead of writing that, I'm going to say that these actually come from take atom, restrict it to the values, and make it a power set of that. You with me so far? So I went binary. Atom is just defining when two expressions are related. So it's also telling us when values are related. All right, so this is just a set, or this time a relation on closed values, which I'm getting out of here. But the only extra restriction that Atom is placing on it is that I'm saying that my values or my expressions have to be well typed. With me so far? Yes?
What does val mean?
Oh, val. Take the set atom, tau 1, tau 2, and when I put the superscript val on it, that means take only the subset which has values in both equations.
So no general expressions, only values?
No general expressions, only values. The value restriction on that. Okay. Now, I'm going to, I just want to make this obvious. When I drop the step index over here, I want to, well, we should be thinking of that as a function from nat to power set of, again, yesterday it was closed values. Are we good with that? Just a function, right? Because I dropped the step index over there. Okay, I just want that notation to be clear. All right. But again, here today we are going to say that we want relations, and relations built out of well-typed values. All right. So let's put that on the side. So the relations that we want should be relations that can accommodate these things that we've been defining. All right. So what we want is rel to be something drawn from functions from the nat to the power set of atom, restricted to values, and in particular, I want I want these things to be relations on values of type tau 1 on one side and values of type tau 2 on the other side. So get to put that here. Okay? I'm just doing basic set theory of functions. All right, so that's for starters the space that these relations are drawn from. Yes?
Are the types to be always inhabited by some value?
Are the types always inhabited?
Yeah.
Okay. Well, the types that we have so far in our language are certainly inhabited. Right? So tau 1, tau 2 are syntactic types, and if you look at what types we have in our language, they are certainly inhabited.
The user can define the rel type.
Yeah, you could define for alpha, right? That's a void type, right? It's not inhabited by anything. But they're not, I mean, so for all alpha, alpha is the void, void, right? It's not inhabited. Ah, but not a value. Yes, yes, absolutely. But this is not an issue. So just, this is an arbitrary relation. It could be empty. Fine. Okay. Now, so we want this relation to be a value relation. It relates values of type tau 1 to values of type tau 2. What else might we want? What other properties might we want this relation to respect? I said that we were going to be sort of, you know, sometimes want to instantiate these R's with these guys. What property did these guys have yesterday? They were downward closed, right? So we want that, or this monotonicity property. So we want that same property here. We want to say that for all k and for all j, if j is less than or equal to k, then R of k should be a subset of R of j. Right, just a shorter form of writing what I was writing. So if v1, v2 belong to R of k, then v1, v2 should belong to R of j. Okay? Or another way of saying it, if two values are related for k steps, then they're related for fewer steps. Okay, so with that out of the way, let's go back. Now what we've done in our interpretation of for all types is we have picked two arbitrary types for the two sides, and we are letting you pick, or letting anyone pick, a relation R that relates values of type tau 1 and tau 2. And from then on, we are going to keep track of that relation R. And you know how logical relations say, if you give me related inputs, I will give you related outputs? Let's take a look at what if we had the polymorphic identity function here, right? I am going to pick two different types, bool and int, to instantiate this function. Right? So I'm taking the same function, applying it to bool on one side and int on the other side. And then I'm passing in true over here and 0 over here. And what will I get? And what I want at that point, if I want to sort of establish that, you know, this function always takes related inputs and gives me back related outputs, the intuition is that you want to set your relation, your R, up in such a way so that it says R is true is related to 0. It could just be that singleton relation, for instance. All right? And then what we're doing is we're feeding related inputs into the function at the type alpha, and we will get back related outputs at the type alpha. Maybe that'll become a bit more clear later. Okay, so now, where?
The R equals set of 0.
Yes, I do need some R. Thank you. Okay, so now I could write this as a set of all values v1 and v2 that belong to rho of alpha, rho, pick out the R, alpha at this step level k. More concisely, I could just write it as, let me write it as a more concise thing, which is just that. Right? So in other words, when you instantiate the alpha in the for all case, you get to pick a relation. When you get to asking the question, you know, as you drill down into this type, at some point when you get to asking the question, hey, here's a type alpha. When are two values related at this type? All you do is you just go ask the relation that you've been carrying around in the row. If that relation says that, yes, these two values are related, then they're related. Yes? Well, so this relation comes up when you try to do examples, right? When you try to do, for instance, a proof of the free theorem that I put up. That's where this method gives you sort of the right points to specify a relation and then use the relation that you have specified to prove the theorem of interest. And we'll see that with the free theorem. General equivalence relation. No, it's not that. See, think of this as like let's take a look at what you would need. Actually, let's come back to that in just one moment. Let's define existential types, and then I want to look at that example, and I think that'll answer your question. Okay? Where do I put existential types? You know, I'm going to erase recursive types and just do it here. Ah. Okay, ink cartridge. I'm probably going to have ink all over me today. Sorry, thank you. I think the cap got stuck. Black, hopefully? Yes.
Why do so what's different for me that we don't put any constraint over R, like it should be reflexive in some way. Because
So you don't. Okay, we're going to come back to this as well. So what you would want from R is only one condition. So if you, I'll give you a technical answer right now and explain it. Okay, technical answer right now is that the definition that we're building right now is good enough without any extra constraints on R. If all you want to do is have a logical relation that is sound for proving contextual equivalence. If you want a logical relation that's also complete with respect to contextual equivalence, so in other words, contextually equivalent, they should be in the logical relation, then you need to constrain the R a little bit more. And we'll come back to that. It needs to observe it needs to respect equivalences. So whenever you put two values, whenever you say two values are related in R, it better be the case that if those values are equivalent to other things, then those things should also be related. So, yes.
Where are we actually using the VK alpha?
VK alpha. Okay, you will use it. You will end up using it. So suppose that this tau, in the concrete case where this tau was actually alpha or alpha, look at what would happen, right? We would be saying that these two terms are related at E of tau alpha or alpha, and then we would go here, and this is now alpha or alpha, and this definition says something about these values being related at the function type at tau alpha or alpha. And now if we unwind the definition of function type, where this is alpha and this is alpha, right here, this will be alpha, and this will be alpha. So it's because the logical relation is defined by induction on type. Eventually, that's your base case, or one of your base cases, along with Boolean. Yeah? Okay. Existential. So when are two values related at existential type? What are values of existential type? Pack. Yes. Okay. So we want to say that a pack tau 1, V1, is related to a pack tau 2, V2, if something. And again, here we're allowing two different types on the two different sides, right? Just like I'm doing in that example up on the board, and we've already talked about this for universals. Okay, so how do you think we need to define this? Look at the typing rule for for pack. The expression that's sitting in the package has type tau with tau prime for alpha, right? So this guy has type tau with tau 1 for alpha. This guy has type tau with tau 2 for alpha. We have the same sort of situation again that we had it with universal types, right? So we basically just want to say that V1 is related to V2. And these are just values, so we don't need to appeal to the expression relation. We want to say that they're related at the type tau with rho extended with a mapping from alpha to tau 1 for the first side, tau 2 for the second side, and now we need a relation R. So basically we want to do, here do we want to say for all R?
No.
We want to say there exists an R, exactly. There exists an R in rel tau 1, tau 2, where tau 1 and tau 2 are the witness types for the two patches. Okay. And we should do for all j less than k out here and j over here. Just like same intuition as before. All right? Okay. By the way, exception mixing or not, logical relations for just pure system F, and existential types without any recursion, non-termination in the language, you would just get rid of everything on the board that talks about steps, and essentially you would have the same set. Okay? All right. So let's extend this to open terms. So far we've been talking about closed values being related and closed terms being related. So what do we need to do for open terms? These terms are open, so they have free term variables, but they also have free type variables. Right? We didn't have this yesterday. So just like we were picking gamma, a substitution that maps our term variables to values, we now have this rho, a substitution which maps our type variables to the types for the two sides, right? The tau 1s and the tau 2s. And of course a relation as well. So we kind of need to close off these terms and then talk about them being related in the E relation. Very similar to what we did yesterday. All right? So, okay, let's define G of empty is just going to be, at K, is just going to be two empty substitutions, right? We're making everything binary, so now we have two substitutions here. I'll just move over here. G of gamma x colon tau with a rho. By the way, we have rows here now because the codomain of this gamma can have types with free variables, right? And those free variables will have to appear in here. So that's why we need to parameterize G, this relation with rho as well, because it contains bindings that close off these. Okay, so here, yesterday we had one substitution, now we're going to have two. So we have gamma 1 maps x to v1, and gamma 2 maps x to v2. Like that? Yeah, thank you. Okay, so these two substitutions are related when gamma 1, gamma 2 are related in G. Let me erase this. Are related in G of gamma for k steps, and the v1, v2 are related according to the value relation for k steps. So very much like yesterday, the row here, except binary. But now we need to say something about how we pick a row to close things off. Okay, so here, basically when we define approximation, we're going to do this sort of similarly to yesterday. First we're going to say, give me an arbitrary k that's greater or equal to 0. And then I want to say, give me an arbitrary row and give me a gamma. Gamma 1 and gamma 2. Gamma 1 and gamma 2 we know have to be related according to this, but we want to impose certain constraints on rho as well, where we're going to require that rho belong to d of delta, that rho be an appropriate substitution given our type environment delta. And we're going to do that this way. So if delta is empty, then rho is simply the empty substitutions. If we have delta alpha, then we want a row that maps alpha to some tau 1, tau 2, and R relation, right? And this is an appropriate thing to pick for this. It satisfies this type environment if, well, first we want to say rho satisfies delta, and the relation that we have just picked, just like we did in the definition of universal type, better belong to rel of tau 1, tau 2. Okay? So basically, this is the point where we, actually, this point and this point in the definition. Those are the 2 points in the definition where we get to, sort of put stuff into row, or start off with stuff in row. And we always have to make sure that whenever row maps any alpha to tau 1, tau 2 r, that r better belong to rel of tau 1, tau 2. And that's all we're doing over here. There's an appropriate value relation that relates values of type tau 1 to values of type tau 2. Okay? And now just to finish this off, we pick a row that satisfies d delta, that satisfies our delta. We pick a gamma 1 and a gamma 2 that are related according to our environment gamma with rho. And if all of that is the case, then we say that our expression E1, we need to close it off, rho 1 gamma 1 E1 is related to rho 2 gamma 2 E2 in the expression relation for k steps at the type tau, carrying around the environment rho, which remembers our relation. Okay. All right, so that is the definition of the logical relation. Now, as I said before, you need to prove that every single one of your value relations satisfy the monotonicity property, right? So if, and this time you're doing it for an arbitrary tau, I won't write it. This time we're doing it for an arbitrary tau, which will include alphas, right? So we need to show that that vk tau is a subset of vj tau whenever j is less than or equal to k, right? Monotonicity. And the alpha case will go through precisely because we have made sure that whenever we put a relation in rho, it is downward closed, right? Rel says that. Okay? And then we basically prove the fundamental property of the logical relation. What is the fundamental property of this binary logical relation? Yes, okay. Fundamental property. Theorem. That whenever some expression is well typed, it must be related to itself. Okay? Does this look weird? Does anyone have questions? Proving that will basically sort of, as I said about the fundamental property yesterday, the first thing you do after you set up your logical relation is you prove this property, which shows you, which is where you end up establishing that the logical relation you've set up is, in a sense, internally consistent, if you will. Okay? Now, that's not all we need, right? Once we've proved the fundamental property, we need to prove, we started out saying, hey, we want a proof method that allows us to easily prove that two given expressions or programs are equivalent, are contextually equivalent. But proving contextual equivalence directly is too hard because it requires you to do this quantification over all possible contexts, and that's not tractable. So this is supposed to be our tractable proof method, but we have to show that it's sound with respect to contextual equivalence. So the next theorem that we want is soundness of the logical relation with respect to contextual equivalence or approximation. And that says that if E1 is logically related to E2 at the type tau, then E1 is contextually, E1 contextually approximates E2 at the type tau. And similarly, of course, the statements for equivalence fall out immediately, right, once we have that. Now, before I say a few words about how we prove soundness, let me just put the statement of completeness up as well. So, completeness of the logical relation with respect to contextual equivalence. So this says that the opposite direction, that if E1 contextually approximates E2 at the type tau, then E1 logically approximates E2 at the type tau. Okay. Let me first say something about soundness, and then I'll come back to completeness, which is a really interesting sort of issue. Okay, so how do we prove the fundamental property? Yesterday I told you we prove it by induction on the structure of this derivation. All right? But the truth is, you don't want to prove it directly by induction on that derivation. At least not right away. You want to prove it you want to stage this proof into two steps. Okay? Step one of this is going to be proving a bunch of what we call compatibility lemmas. All right? So the compatibility lemmas are essentially a generalization of of each of the cases that you would prove for the fundamental property. Let me explain what I mean by that. So the compatibility lemmas for the language that we have up here would be compatibility lemmas that we want to prove. So the first compatibility lemma that I want to prove would be X logically approximates itself. Well, that's a really easy one. That's exactly what you would prove if you were directly proving the fundamental property, so there's nothing different yet. Here's another one. Let's consider the lambda case. So I'm going to write it as an inference rule, but really I mean that the lemma that you want to prove is if the stuff above the line holds, then the stuff below the line holds. Okay. But the inference rule allows you to see that they're really just a generalization. They're coming from the structure of your typing rules. Okay, so I want to prove that gamma x colon tau1 dot E1 logically approximates, did I say gamma? Lambda. Lambda x colon tau